These are applications of derivatives. And implicit differentiation. These are scenarios when two or more things are changing. I'm going to say remember to take the derivative of every variable. Sorry, my hand's cramping up, my printing's getting bad. Okay, so this will be things where multiple things are changing in a question. Okay, so it will not just be the angle is changing, the angle will be changing and the distance is changing, which sort of makes sense. Okay, or if you're dealing with, the question they like to do in this is you're dealing with a pool of water, like if you think of a swimming pool, and the swimming pool is draining. What's the height of the pool? The height is changing as the amount of water is changing, and all sorts of fun things like this. Okay, so it's multiple things are changing at the same time. These are prime calculus questions for the present and the future for you. Okay. This is an application of implicit differentiation. Okay, so this is the application of what we just did last week, whenever this was. Okay, that's it. Here we go. My suggestion, although I didn't write it on the board, this is for those that are listening to me right now. The suggestion is to write out everything you know. I'm going to treat this back like you're in grade 9 for a second. Any information that you're given, please write it out. Okay, I'm not going to make you declare your variables. It wouldn't hurt though. Okay, right? But you should be thinking about, actually I'm going to declare my variables. There you go, example 1 says, air is being pumped into a spherical balloon at a rate of 5 centimeters cubed per minute. Determine the rate at which the radius is increasing. When the balloon is 20, when the diameter is 20 centimeters. Okay, as we do this, Evan, I hope you're at least mentally taking this down, right? Okay. This is something where there are multiple things changing, okay? This is a calculus question because remember that first difference is rate of change. Okay, so we have two things changing in this question. I'll give you a second to scribble down here so I don't take saves. It's not every day that I teach Michael something. This is like the first time in a year. So good. All right, so could somebody tell me there are at least two things changing in this question? Okay, what are the two things that are changing? Volume, okay? So I'm going to say dV by dt. What that means is the rate at which the volume is changing. Okay, so what's the rate that the volume is changing? It's going to be what? 5 centimeters cubed per minute. So I'm just going to say dV by dt is going to be 5. Okay, so the rate of change of volume is going to be 5. Are we okay with where that came from in the question there? Yes? Okay, what else is being changed in this question? the radius, okay? So I don't actually know what the radius is, okay? But the reason this is a calculus question is if you think, if my radius is this big, and I'm putting in 5 cubic centimeters per minute, how big is it, how fast is it going to be increasing? Not a whole lot. If my ball is this big and I put 5 cubic centimeters per minute, it's going to be a lot more, right? So the rate of change of the radius is going to depend on how big the ball actually is here. So dr by dt, that should be a small r, sorry, I love capitals, sorry, is unknown, which is the rate of change of radius. Okay. And that's what we're actually ultimately looking for in this question. There's one other piece of information, someone other than Michael here. What else do we know about this question? There's one more thing we know. We'll play along. Sorry? Good. So we can get the equation here in a second. Before I get to the equation, we'll give them one other piece of information though. Diameter is 20 centimeters. What does that mean my radius is? Good. So my radius is going to be 10. So I need an expression for volume. Can anyone recite what the volume of a sphere is going to be? If you can't, that's okay. This is why God created phones. Yeah, go ahead. That is the volume of a sphere right there. Now, can somebody suggest how I proceed from here? Not yet. Because that would just give me the volume if we were to do that. Right? We could find the volume and say, how can I proceed from here? Take the derivative. Good. When I take the derivative, I'm going to be able to guess for myself when things are changing. So, can somebody please tell me what the derivative of v is going to be, please? dv by dt. Good. Or v prime, but we'll get to that in a sec. Now, this is why math is magical. Can somebody tell me the derivative of 4/3 pi r cubed? Go ahead.
4 pi r squared.
Wow. Very good. Isn't that beautiful? Okay. Because what we're doing is here, the thing, okay, let me slow down here. All of our calculations here are dependent on time. Okay, right? So if you think of how much the volume is changing, it's per second, right? So or per minute, sorry. Okay, because everything is per minute and the rate, so everything's going to be related to time there. Which is the funny thing about this question, because even though time's not in this question, the derivative is the rate of changes as compared to time. Okay, great. So how do I solve for dr by dt? That's my unknown. What can I do? So that should turn into dr by dt equals 5 over what? I want to call that 400 pi, which is 1 over 85. I'm going to slow down, and I'm going to give you guys a chance to ask questions here before I continue here, all right? So just like any question for derivatives, you just take the derivative, okay? You're looking for a rate of change. We're getting the original, we know the original equation for velocity. Now, we were asked to, somebody should shout out to put in 10 per r. The problem is that would just give us the volume, right? It wouldn't give us the change in volume, all right? So, and this is isn't this beautiful about math? Doesn't it just make you happy going from here to here? It makes me happy. Okay, right? Because everything's related. That's great. All right, I'm going to give you guys one to try yourselves here right now, which will be example 2. Okay, I want you to struggle away a little bit with this. Or is that too tricky? No, it's not too tricky. You guys can do this. It is tricky. You guys can do it. Example 2. A 15-foot ladder resting against the wall. The bottom is initially 10 feet away from the wall. And is being pushed toward the wall at 1/4 feet per second. How fast is the ladder rising? 12 seconds after we start pushing. Okay. I'm going to let you struggle with this for about 5 minutes, and I'm going to take it up. What I will suggest that you do is draw a diagram. Diagram's where to start. Think of what your unknowns are. Think of what your variable is going to be as far as what's changing and what's not. Okay, so set it up like last one. Remember we had dv by dt, dr by dt, and r and stuff like that. Anything you know, start off with a diagram. Can somebody guess what type of diagram this is going to be if it involves a ladder against the wall? Triangle, very good, Michael. Okay, right? So start with the triangle, please. That would probably help. Okay. Matt, you know what you impress me right now with our ruler for your triangles? Maybe if I were to do that, my triangles would probably look good on the board, the smart board. Jeff, you're shaking your head, but my triangles are awful. Just before we get too far, who doesn't have that photocopy of these questions homework? The last one they gave you good. One. That's it? Everyone else has one? Michael, once you're done this question, I need you to make a photocopy for me. This question. Okay, so if you're wondering what the question was, this is it right here, guys. This is here. So 2 people I have up to now. All right, do you still need more time to struggle? Oh, sorry, John. This is Michael here when he's done. There it goes. We're going to give you approximately 2 minutes to struggle with this still. If your page is blank, you should have a triangle drawn on there. Is there something like, I'm using x and y is what I'm using for my 2 side lengths? You should have something like maybe dx by dt, dy by dt, those are things you need to be thinking about this question. Okay? Hypothetically, I can answer that hypothetically. They really do calculus a good time. It's really awesome. Your brain is going to grow so much. How they do it? How they say they do it in English? Oh, like the wording. Whatever foot percent you represent. triangle. That's all I can do. We can do this. Yeah, let's start over. All right. Are you ready to try this? Okay, because this one's a little bit tricky here. Okay. So what we're doing, are we okay with what I got the diagram here? So the idea was I'm pushing dx by dt with the speed that I'm pushing it towards the wall here. As I push a ladder, I'm going to use this meter stick as an example. Okay. Can you hold your hand up, please? I promise I'll give you slivers, okay? So here we go. As I push the bottom closer, the idea is the top is going higher and higher and higher. Okay, that's what we're looking to calculate. Okay. The idea, the reason this is a thank you. The reason this is a calculus question is because you have two things changing, right? Depending on the input, the output's going to change as well. Okay, so let's get a few different things that are in here. Can somebody tell me anything that they knew from this question they wanted to put in here? What do they know? Good, wonderful. Anything else? Yes, originally. We're going to leave that for right now. That will come into effect eventually. Okay. What else do we know? Yeah. I'm going to say then dx by dt. I'm going to call it negative. You can call it. I'm going to call it negative 1/4. Okay. What are we actually looking for? Because it's going to the left. What else are we looking for here? What are we looking for? Right? dy by dt. Now I'm going to use unknown. Okay. So it says here, how fast is the ladder rising 12 seconds after we start pushing? We know the initial speed. I'm going to write that down here. The initial x is equal to 10. What's the x going to be after 12 seconds? How do we calculate what our x value is going to be after 12 seconds? And first of all, why do I need that? What would that give me? Sorry? How'd you get that? Yeah. So after 12 seconds, good. So after 12 seconds, x equals 10 minus 1/4 times 12, x equals 10. We're going to need that in a few minutes. You're good, Michael? Okay. You're going to need that in a few seconds. Okay, so how can I solve, what equation are we going to actually use for this one? Very good. Where did you get the idea of Pythagorean theorem, Laurel? It is a right angle triangle, okay? And so I'm going to write in here just x squared plus y squared equals 15 squared. All right. From there, you guys want to try and take it from there? Yes, you do. Now I've set it up for you guys right now. Yes, please. I've set it up for you guys right now. I want to know dy by dx is dy by dt is what I'm looking for here. Okay, so after this is a good start for you guys, okay? We're solving for dy by dt is what we're solving for. We can probably get a value for y here too. But yeah. We can get a value for y probably too after. Looks like there's one thing we're still missing here. I'm gonna 1, 2. One thing I didn't give to you, but since you guys are calculating, you should be able to figure this out. I probably also still need the value for y, right? How would I get the value for y? Nobody knows how to get the value for y? You guys are thinking way too deep. Theorem again, right? So I'm going to take the root of that, so I'm going to say 7 squared equals plus y squared equals 225. So that's a y equals when you need it. We're going to need that near the root of it. Right, 176. Read a question then? Yeah. Yeah, if you were to do that, yeah, that would work. Oh boy. That would work, wouldn't it? Yeah. Because there's actually a plus or minus inside the square root, right? Because I think the square root, when you do y equals, you square root of 0 plus or minus root. So just do it my way and get this. Okay, good. Okay, who needed all those papers? All right, let's start to take this up here. Let's start to take this one up. Okay, can someone please, other than Michael, take the derivative of x squared, please? Close. Okay, now this is different because we're relating things to time here, right? Okay, so that's where that comes in there. What's the derivative of y squared going to be? Good. Equals 0. The derivative number is going to be 2. All right. What am I actually solving for in this question? dy over dt, everything else I can sub in for. Can someone be brave and start subbing in? What does x equal? Good. What does dx by dt equal? Good. So it's going to be 2 times 7 times negative 1/4 plus 2 times root 176 dy by dt equals 0. Over here I'm going to say 2 root 176 dy by dt equals 14 over 4. So dy by dt Okay, other than Michael, did anybody get that or close to it? Oh goodness, nobody. Okay. We're doing another day of this. Today and tomorrow is going to be suffering. Word problems. Okay, and then on Wednesday and Thursday we'll move on. Wednesday we'll go into the laws of logarithms, and then Thursday will be derivatives of logarithms.
Mr. Sadler,
Yeah.
that could also be said like 7 over 16 to 11.
Put it, Michael.
So
I'm
you
so
could
glad
do
you're a
that.
student. I'm so glad you're a student today. 7 over 16 root 11. Thank you, Michael. Now, this is tricky the first time, second time through. Understand the logic of what we did here, though. The tricky thing is the setup of the question here. All right, so the idea is to write down what's your given information that's changing? Okay, what constants you know? This question was more difficult than the first one because you defined your x and your y yourself, right? Once you had your x and the y yourself, then it was just basic derivative. Yeah. 7 over 32 root 11? Oh, I think because it was 14 over 32 root 11. Right, so I think I'm happy with 0.1319. Okay, but that's fine.
Yes, okay. Yeah,
All right, here we go. You ready for the difficult question now? Yes.
Is this velocity or is this acceleration?
Velocity, that would be. Velocity.
Sadler, Sadler.
What's that? Michael's or mine? Too bad. Here we go, example 3. It's going to say two people are 50 feet apart. I'll do this one as a class too. One starts walking north. So that their angle is changing 0.01 rad per minute. At what rate is the distance changing? When theta Okay, I'm going to give you the diagram for this one. Oops. Yeah.
So it starts at 0.
Yeah. Yeah, because we're going to be like 50 feet apart. So the idea is, Michael, if you and I were like looking at each other, that's 0, and then again, as you're walking, every minute it's going to be 0.01 rate. It's going to be. All right. I'm going to get you set up on this one. We'll solve this as a class. Okay. I'll give you a second to scribble. Okay. The key to these questions is giving your given information at the beginning. Okay. So I'm going to let everyone struggle, and then I'm going to ask for one volunteer from each row. The middle row, you guys are quiet. Luckily, you have Michael here today. So, Michael, you're out though. Okay. I get one volunteer, and you will answer for your row. And one volunteer tell me a piece of given information from this question. Is there anything that we know? Anybody here? Nothing. Aim. Yeah, good. So how do I write that? d theta by dt is equal to 0.01. Very good. Oh, this reeks trig, this question, doesn't it? Doesn't this smell like trig?
Ew.
Only a trig tester right
I'm
soon.
allergic.
This could help you with this question. Okay, first row's out. Thank you. That's a team approach. What else do we know? What else do you know about this question? Is there anything else I know? The second two rows. Michael, go.
D is 50 over cos theta.
Okay, you're way ahead of the game. Stop right there. Not yet. It will be in a sec. Okay, but you're way ahead. Take 2 steps back. What else do you know with this question? You know a few more things. 50 feet apart. Okay, good. What else do we know, though? Well, hopefully somebody's going to say this. Okay. All right, so as this goes here, I'm going to say, as Michael said here, cosine theta equals 50 over d. So I'm going to say d equals 50 over cos theta. What do we actually... There's one other thing that I need here in this question. What's the last thing that I need in this question? What am I actually solving for? Somebody in the back row. What am I actually solving for? In the back row. What am I solving for? Okay, now I would treat you like you're in grade 9 here. Read the last sentence. That will tell you what we're looking for. The rate distance is changing. What can I call that? I shouldn't call that D. I should call it something else. Call it X. dx by dt is what I'm looking for. What that's going to be, the reason I didn't want to call it D because dB doesn't really make a lot of sense here, okay? Alright, so what you're actually looking for is the rate of change of distance. Why does this equation that Michael gave to us look like it's going to work out quite nicely? Yes? Okay, but if you look at our given information, you have to use all the pieces of given information here. When you take the derivative of x, you're going to get dx by dt, which will work. When you take the derivative of cos theta, you're hopefully going to get a d theta by dt in there, hopefully. Okay, that's the dream. Right? Okay, so what you guys should be doing right now is this. And everyone, I want everyone in the class, because I heard that some people that you were stressed out about the test. Can everyone please take the derivative of that right there for me? Don't be stressed out, Joe. Lucky my ears are bad. I'll be yelling at you right now.